Hello and welcome back to Physics Galaxy, and this is lecture number 7. And today we're going to discuss the method of images, and we'll also discuss some relevant problems regarding this topic. So in the previous lectures we were discussing the Poisson's equation del square V equals to minus rho over epsilon naught, right? So this was our Poisson's equation, and we tried to solve this equation in different conditions when rho equals to 0, and we also use some boundary conditions, okay? In different Cartesian spherical and in cylindrical systems we solve this equation, right? And today we are going to use a method of images, and in this method of images we are going to use combination of real and imaginary charge distributions, combination of real and imaginary charge distribution. So combination of real and imaginary charge distribution, so that they satisfy so that they satisfy our boundary condition. They satisfy our boundary conditions. Now, as we have already discussed in the uniqueness term, that if you find a solution to this equation, del square V equals to minus rho over epsilon, if you find the solution to this equation, okay, and if that solution satisfies your boundary conditions, then that is the solution. You don't have to find the new solution, okay? So what it means is that if you find your solution by any method, whether you use some guess, whether you use some trick, or you use some analytical methods, okay, so it doesn't matter how you get that solution. If that solution satisfies your boundary condition, then that is the solution. And today we are going to use some cheating to find our solution, and we'll see that solution will satisfy our boundary conditions, and that will be the solution. Okay, so today's solution, it will be some kind of a cheating solution. Okay, now let's before we discuss the method of images, first thing you should note that we'll be discussing only two region solutions. Okay, two region problems. Okay, so by that I mean that you will have two spaces. Okay, suppose this is an infinite conducting sheet. Okay, now I will have the right space and I will have the left space. Okay, in the right space I will put some real charge, okay, q, and in the left space I will have my imaginary charge. Okay, so there are two regions. The region where I have my real charge, okay, so this region is my space where I have my real charge, and this is the space where I have my imaginary charge. Okay, so remember one thing: the imaginary charge has to be put in the different space other than the space where you have your real space. Okay, we cannot put the imaginary charge in the space where you have your real space. Okay, similarly we'll have problems like conducting spherical shell. Okay, so we'll have inside space and we'll have outside space. Okay, outside space, and we'll put our charge, suppose real charge, in this sphere here. Okay, so this is my real charge. Now where should I put my imaginary charge or the image charge? That has to be put in this space. Okay, inside wala space. Okay, here I will put my q dash. Okay, so suppose if q is my real charge, then in this lecture q dash will be my imaginary charge or image charge. Imaginary or image charge. Okay, so imaginary charge or image charge has to be put in different region. Okay, not in that region where you have your real charge. Okay, so with this understanding, let's move on to problems directly. Okay, one more thing. So suppose this is my um, infinite conducting sheet. So it's a basic example. So whatever my charge distribution, okay, suppose this is my q1, this is my q2, this is my q3, or any weird charge distribution, or any dipole, suppose this is my p1. Okay, so you may have any kind of charge distribution. What you have to do? You have to find the mirror distribution. Okay, Suppose this is q1 here, q1 dash. Similarly here you have q2 dash. Similarly you will have here q3 dash. Okay, and we'll have something like this. Okay, q dash if this is q, and similarly you will have dipole like this p1 dash. Okay, so you just have to do some kind of mirroring. Okay, as if there is some mirror. Okay, as if there is some mirror in place of infinite conducting sheet. So you have to do this kind of mirroring thing, okay, in these problems. So let's take one example that's called infinite charged sheet. Infinite conducting sheet. Infinite conducting sheet. Conducting sheet which has been grounded. Okay, which has been grounded. That means, suppose this is my sheet. Suppose this is my sheet. Okay, it's an infinite, it extends to infinite. Okay, and it has been grounded. That means potential equals to 0, v equals to 0 at all points. Now, and suppose I have a charge q. Suppose I have a charge q. Okay, and suppose its coordinates are x equals to 0, y equals to 0, and height equals to, or z equals to d. Okay, now in the method of images, what I will do, I will put my charge, imaginary charge, in the different space so that the potential is satisfied. Remember, potential at all points equals to 0. So if you look at this point, v equals to 0, here v equals to 0, any point you take on this infinite conducting sheet, potential equals to 0. So it seems that if I put my charge as here, q dash, which equals to suppose minus of q, then this combination of this charge and this charge will satisfy the boundary condition, right? So it will satisfy my boundary condition. Then that means this combination, suppose if I take this is my plus q, this is minus q, if I take any point, suppose p point here, the potential due to this charge and potential due to this charge will give me 0, because the distances are same basically and the charges are opposite. The potential at this point p, if I write v equals to u divided by 4 pi epsilon naught, so this is d, this is d, and the potential due to q dash will be minus q divided by 4 pi epsilon naught d, which equals to 0. So if you take any point now, suppose this is another point, okay, potential due to the real charge and the imaginary charge will be 0 on all points, okay, in this infinite conducting sheet. So that means this real and imaginary charge distribution will give me the potential at any point. Okay, because it satisfies the boundary condition. Yes, it satisfies the boundary condition. Then that means if I take any point, okay, if I take any point, then this combination will give me the real potential. Okay, and one more thing to note here, you can't find the potential in the region where you have your imaginary charge. Okay, you can find the potential only in the region where you have your real charge. Okay, right. Now let's solve this example in detail. Okay, okay, so I have this infinite conducting sheet whose potential equals to 0, v equals to 0. I have my charge q here at a distance of 0 0 d. Okay, and my imaginary charge is q dash, okay, which equals to, we know it's equals to minus q, right, minus q, and it will be at a distance of minus d, 0 0 minus d, right? So if I take any point p here, suppose if I take any point p here, then what I have to do to find the potential at this point, simply find the potential due to real charge and the potential due to the imaginary charge, right? So potential will be the potential due to the real charge plus potential due to the imaginary charge or image charge. So this is the solution. Okay, but we have to check that whether this combination satisfies the boundary condition. Yes, we have checked it, it satisfies the boundary condition. Now let's find the solution. Okay, we know this is the solution, but we have to we'll see more things related to the solution. So now let's write the solution in full form, because this comes in many competitive exam. So v real equals to 1 by 4 pi epsilon naught q divided by the distance, this distance, right? And that distance, suppose if this coordinates is x, y, z, then I will write simply under root of x square plus y square plus z minus d, z minus d whole square. Okay, so this is the potential due to real charge, and the potential due to imaginary will be simply minus q divided by 4 pi epsilon naught under root of x square plus y square plus z minus d, that means z plus d whole square. Okay, now this is the solution. You can simplify it a bit, okay, but this is the solution. That means if I take any point in this region where I have my real charge, okay, this will give me the potential. And you can check whether this solution satisfies the boundary condition. Yes, because if you put z equals to 0, z equals to 0 here and here, this cancels out, right? So this is the solution. Our uniqueness theorem guarantees that this is the solution. Okay, so the solution that we got, okay, let's write v of x, y, z. V of x, y, z equals to, let me take q common and 4 pi epsilon common. So my solution is q divided by 4 pi epsilon naught. Then I have, okay, then I have 1 divided by under root of x square plus y square plus z minus d whole square, z minus d whole square minus 1 divided by under root of x square plus y square plus z plus d whole square. Okay, so this is my solution. Okay, so how we find the solution? We found it just by taking an image charge, okay, at the same distance. Okay, so this was d, we took this at the same distance d away from this, and we said we uh, uh, said that it satisfies the boundary condition, and this was the only solution. Okay, now if we got our v, then we can find electric field also, right? And electric field comes simply taking the derivative, okay, that is, or the negative gradient of potential, negative gradient of potential. Now you can do the gradient of this complex function. So let's do that because it comes in problems. Okay, okay, so one thing to note here is that because I have an infinite conducting sheet, okay, and the, here is my imaginary sorry, real charge q, and the electric field due to this charge will be like this. And when it, the electric field lines comes close to the metal, it will be perpendicular. Why perpendicular? So they will be perpendicular. Okay, so this will be the electric field lines of my space, okay, real space where I have my real charge. Remember that the electric field close to the metal will be perpendicular. Okay, so if you can zoom out, so this will be perpendicular. Okay, yeah. It will be perpendicular always. So let's see why it's perpendicular. Okay, when we have metallic surface, suppose this is my metallic surface. Okay, metallic surface, metallic surface. So I'm saying that metallic surface, on metallic surface electric field is always perpendicular. Why? Let's just suppose that this is my electric field. Okay, suppose this is my electric field which has both normal component. Okay, suppose this is my normal component E n cap, and this is my tangential component E, suppose T cap. Okay, normal component and the tangential component. Then I am saying that this tensional component will drive the electrons, okay, in this metallic surface, and that motion of electrons will cancel out the electric field. Okay, so the only electric field component will, that will remain is the normal component. So in any problems when you are finding the metallic, so when you are using the metallic conductors, then the electric field at the interfaces, okay, or the surfaces of the metal is always perpendicular. Okay, so that means if I have to take the gradient, I will take the gradient with respect to z only, that means minus dv by dz. Okay, so that's why we should not take the electric field with respect to x and electric field with respect to y, because that will come out to be 0. Okay, right, so let's take the, let's find the electric field for this case. Okay, so that means we have to take the derivative with respect to z. Okay, let me do it here. So our potential v equals to 1 by 4 pi epsilon. It's a good exercise if you do this calculation once. Okay, then we have 1 divided by, let me write it like this, x square plus y square plus z minus d whole square to the power 1 by 2, okay, in place of under root, minus 1 divided by x square plus y square plus z plus d whole square to the power 1 by 2. Okay, to find the electric field, I just do minus dv by dz. Okay, and this will be in the direction of zk. Right. So I have minus and 1 by 4 by epsilon naught, and then I have to take the derivative of this term and the derivative of this term. So if you do this, so it will come out to be 1 by 2. Okay, actually minus 1 by 2, then x square plus y square plus z minus t whole square to the power the minus 3 by 2, then the differentiation of this, that will come out to be 2 z minus t. Right, then we have this term, so minus to become plus 1 by 2 x square plus y square plus z plus t whole square to the power minus 3 by 2, then 2 times z plus t. Okay, so this is my electric field. You can solve it a bit. Suppose 2 and 2 cancels out, 2 and 2 here cancels out, and okay, but I want to find the electric field at when z equals to 0. Okay, z equals to 0, right? So electric field at z equals to 0 will be so here I will get minus minus will become a plus, so I will get a 1 by 4 pi epsilon naught, then I will have d divided by x square plus y square plus z minus t whole square to the power, sorry, z is 0, so z is 0, so simply d square to the power 3 by 2, then minus minus um, minus d divided by x square plus y square plus d square to the power 3 by 2 plus 0, and my electric field, here we have minus, so electric field will be simply minus 2d divided by 4 pi epsilon naught x square plus y square plus z square to the power 3 by 2 in the direction of zk. So my electric field is in the z-cap direction. Okay, as we have already seen here. Okay, so it's in the downward direction, right? Okay, so the electric field is like this. Now if you have our electric field, we can find one more thing, that is we can find the surface charge density, right? So I forgot one charge I'm missing, so q, so here it's q and here it's q q d. Okay, so this is my electric field. Now if I have my electric field, I can find surface charge density. Surface charge density. So how can I find the surface charge density? Okay, so one thing you should be clear, that because this is an infinite conducting sheet which is at potential 0, that doesn't mean there will be no charges, okay, present on this infinite conducting sheet. There will be charges present, obviously, so we had to find that. Okay, so let's find that. So because if I have metal, suppose this is my metallic surface. Okay, remember, if I want to find the metallic charge density on the surface, so suppose there is some charge density sigma. Okay, then what I'll use, and this is metallic part. Okay, what I will use simple Gauss's law, which I already discussed. Suppose this is my Gaussian surface. Inside, electric field will be 0, right? Outside, okay, it will be perpendicular, E and cap. So integral E dot ds will be charge density inside, that will be sigma A divided by epsilon naught. Now electric field times ds will be simply E times sigma plus E times sigma. So this is outside, E out, E in, equals to sigma A by epsilon naught. Now sigma in, sorry, electric field inside is 0, so my electric field that is outside will be simply, so this is A. 1 2 3. So we'll use Gauss's law. So integral E dot ds equals to charge inside, that will be simply sigma times A, that A is the area of this, okay, divided by epsilon naught, and EDS will be simply EA equals to sigma A by epsilon. Why didn't we include the flux from this surface? Because there is no electric field. So AA gets cancelled, electric field equals sigma by epsilon naught, or we can get sigma as epsilon times E. Okay, so if you had to find the charge density in case of metallic surfaces, you find what is the electric field on that metallic sheet, then multiply by epsilon naught, that will give the charge density. Or if you have potential, so sigma will be equals to minus epsilon naught dou V by dou, or dV by dN, right? So these are two formulas which will give you the charge densities. Okay, now I have my electric field. Now let's find the charge density. So my electric field is, so my electric field at addition z equals to 0 equals to uh, 2qd minus 2qd divided by 4 pi epsilon naught x square plus y square plus d square to the power 3 by 2, right, to the power 3 by 2. Okay, this is my electric field at the interface, or at the surface of this infinite conducting sheet. So what is charge density? Sigma charge density will be simply electric field times the epsilon naught. Simple. Okay, and you can also find the total charge on this infinite conducting sheet. Okay, so you can find the total charge, that will be integral sigma dA, and if you evaluate this integral, that turns out to be minus q. Okay, so we have real charge q in front of this infinite conducting sheet, then that means there is a developing of charge. Okay, so there is a develop of charge, okay, onto this surface. Let me use another color. So there is some charge here, and if you integrate this whole charge, it will come out to be minus q, right? And if you look at this charge density, because the charge density is simply minus 2 epsilon naught qd divided by 4 pi epsilon naught x square plus y square plus d square to the power 3 by 2. So that means when x and y equals to 0, it's maximum, right? So there is maximum charge here, maximum negative charge. Okay, so here we have maximum negative charge, and then it drops off, and at infinity it's almost to 0. Okay, so this is all negative charge. Okay, this is all negative charge. Okay, so which is intuitionally correct, right? So if you have charge q, it will pull some negative charge, but at the same time you should remember that there will be also some positive charge, okay, and that will be uniformly distributed in the backside, positive charge. So this is the actual charge distribution of this. Okay, and it is, remember, it's at the potential v equals 0. Okay, so we have solved this problem completely. Also you can also find the electric field lines. So electric field lines, as we know, equals is like this. Okay, and it goes like this in the upper portion. Okay, so there are no electric field lines below, no electric field lines here in this region. Okay, Now you may ask, but there are charges, positive charge here, but there is also equivalent amount of negative charge here, so they cancel out in this region. Okay, so this is, and now let's go back to different problem. I will not do all the calculations. So this is a problem regarding the conducting. No, before going to spherical surfaces, let me do one more thing. Suppose if you have again infinite conducting sheet. Okay, let me draw it like this. Suppose this is an infinite conducting sheet at potential V equal to 0. Now what happened? We have solved for simple charge. Okay, point charge Q. What happens if I have an infinite charge density lambda? Okay, we have line charge density lambda. Okay, the image will be simply same configuration with a minus lambda. Okay, and if what about at dipole? Suppose if I have dipole at this, okay, p, then its image will be exactly like this but opposite. Okay, so it will be suppose like this. Okay, just image of it. So in case of infinite conducting sheet, you just have to use some imagination, and you have to think like that this infinite conducting sheet acts as a mirror. So for positive charge, you have to go to minus q, and you have to see how the configuration will look like as if there is a mirror. Okay, right. Now let's go back to now original different example, that is in conducting shell. Okay, or grounded conducting shell. Grounded conducting shell. So I will not solve this whole problem. So suppose if I have a grounded conducting shell, okay, and suppose my charge at a distance of my charge, real charge is q, and let's suppose that it has a radius capital R. Okay, capital R is the radius, and the distance from the center to the charge is a. Okay, then my imaginary charge, where should I put my imaginary charge? Like now there is a little calculation. So you have to imagine that I have my charge q dash at a distance of suppose r dash. Okay, and you have to satisfy the potential at all points. Okay, basically what you'll do, you'll find the r dash and q dash by solving the potential at this point and this point. Okay, and if you solve that whole algebra, you will get q dash equals to minus q of it will be r divided by a. Okay, and similarly for r dash will be r square by a. Okay, so what you have to do if you want to get your results q dash and r dash, you solve for this point. Okay, suppose take this line, okay, connecting center of your spherical conducting shell with the charge q. Find the potential at this point p1, and find the potential at this point p2 using your charge q dash at a separation r dash. So from p1 you will have one equation, and from p2 you will have different second potential. Okay, so two potentials will give you two unknowns, r dash and q dash. Okay, if you solve that, you'll get these results. Okay, now one interesting thing is to note, what if I have real charge inside? Okay, so suppose what if my real charge is inside q? Q is my real charge. Then what will be the value of imaginary charge? Okay, so then imaginary charge will be outside. Okay, q dash. Okay, and you just have to inverse it. Okay, So r by a, you have to take a by r, q a by r. Okay, reciprocal, you have to do the some reciprocal thing here. Okay, similarly r dash, that is the distance of the imaginary charge which will be outside, that will be a square by r, a square by r, right? Okay, so you just have to do this reciprocal.